Welcome to another lesson in Math 8. This is Unit 7, Lesson 10, representing large numbers on the number line. We're going to learn about how we can see really big numbers on a number line. As you can tell, this number line goes from 0 to 10 to the 7th power. This is a very large number. This is actually 10 million. So if we're going to be looking at this number line, and we are going to be equally distributing the values between these values, I think it's really important that we understand that this value is 10 million. And as we recognize that this value is 10 million, this can help us to understand that these little segments in here can be broken down into 10 times smaller values than 10 million value, or than 10 million. We might count the tick marks and think, okay, 10 to the 7th is being divided into 9 or 11 parts, but we don't want to be counting the spaces between. We want to make sure that we're recognizing that the segments are the values that we're looking at. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This would be the 10th one. This is very important today because we need to recognize that the values that we count inside of here have to represent the values that are in between here. So you might be tempted to just say 10 to the 1st, 10 to the 2nd, 10 to the 3rd, 10 to the 4th, 10 to the 5th, 10 to the 6th, 10 to the 7th, but then we end up with a gap. What we really need to be after is this. The idea is that 10 to the 7th power can be broken up into 10 parts, thinking more specifically about 10 million. Now that I've talked a lot, let's talk about what that looks like. What we need to pull these out, or what we need to do with these values, is we need to break this down to the next set of values. When we take 10 million divided by 10, that makes our value equal to 10 to the 6th power. Consider that we've talked about quotient of powers. 10 to the 7th power divided by 10 means that we will take 10 to the 7th minus 1, which equals 10 to the 6th power. So that means all of these values in here would be 10 to the 6th power. That's not it. That's not all of it, though. What we need to recognize with this is, now that we understand that that's 10 to the 6th power, what we can do with this is start counting these values. And looking over here, we would say this is 1 times 10 to the 6th, and 2 times 10 to the 6th, 3 times 10 to the 6th, 4 times 10 to the 6th. Of course, we'll continue our pattern. And then we start back up here at 1 times 10 to the 7th. Now, this might seem, let's just look and understand what these are. From here, we know that 10 to the 6th power is equal to 1 million. And now with that understanding, we can recognize that this is 1 times 1 million, so this makes 1 million, and 2 million, 3 million, 4 million, 5 million, 6 million, 7 million, 8 million, 9 million, 10 million. And we can see that that numbers line now logically opens up and expands to the values that represent these exponential values. Each of these exponential values are written in a scientific notation, which is something we are continuing to go ahead and learn. We look at the equal parts, we look at those values and see how it's divided out to make it all work out for us. Okay, so let's go ahead and we'll move on to 10.2. In 10.2, what we're looking for is we're going to be comparing these number lines. There is an interactive version if you'd like to open up. We are going to be putting these numbers on the same number line as before. You'll notice that it is here. We need to recognize that this is, again, 1 times 10 to the 6th, 1 times 10 to the 7th. Whoops, just kidding. 2 times 10 to the 6th. 3 times 10 to the 6th, or each of these, as we know, are now millions. But it'd be hard to write all those millions in there because there's very limited space. But we have to recognize that the intervals, is what we call this, are in the millions. And when we recognize that these are in the millions, we can start placing these numbers on the number line in their appropriate values. So when we see 4 million, we would put A right here. And then B, we have 5 to the 6th power times 10 to the 6th power, which we know is 5 million. So we can put B right here. Then we see C where it says 5 times 10 to the 5th power. This would be 5 times 10 to the 1, 2, 3, 4, 5, which is only half of a million. And so we need to come back into here and recognize that this value would be half of 1 million. So we could recognize point C would be here. Point D, 75 times 10 to the 5th. So let's write this as 75 times 10, 10, 10, 10, 10. And we see that that is 7.5 million. So we'll put value D right here. Value of E, we see 6/10. So we're going to go ahead and move that decimal 1, 2, 3, 4, 5, 6, 7, or 10 or 7 powers of 10 larger, which tells us that 6/10 times 7 is actually equal to 6 million. And so we have a value right here. All right, hopefully that's following along pretty well and easy and tracking pretty closely. Let's go ahead and turn the page. It says train number lines with a partner and check each other's work. How'd they do? Decide where numbers are placed. If you disagree, that's okay. We won't be able to do that today. So the question is, which is larger, 4 million or 7.5 times 10 to the 5th power, or 75 times 10 to the 5th power? Estimate how many times larger. If we go back to our number line and we recognize these values, so we're comparing specifically A and D, and we recognize that on the number line, A is much smaller than D. That's okay. We can recognize that piece and we can simplify that value to say that I understand that 75 times 10 to the 5th is 7.5 million, whereas A is 4 million. And so we say that 4 million is less than 75 times 10 to the 5th power. Estimate how many times larger. This is a really key phrase right here. When we say how many times larger, we're indicating that we need to use division to compare these values. Now, what we can do with this is we can take our values and look at it as much smaller numbers. So looking at these as powers of 10, we can actually write this one as a power of 10, or write it as 40 times 10 to the 5th power. And then I can just use my quotient of powers concept to do the division. And from here, what I recognize is 10 to the 5th divided by 10 to the 5th. That's the same number divided by the same number. So that's just 1. That just leaves me with 75 divided by 40. I know that 75 is close to 80. So I know this is going to be close to 2. What I can say as far as an estimate, if I'm going to estimate without calculating, I would estimate this is about 1 8/10, perhaps a little bit more, just because I want to make sure that I'm right on with it. I'm going to check. I want 75 divided by 40, and I see 1 875 thousandths as my exact value. So my estimate was pretty close, but obviously I can get closer. Okay. Another one, the speed of light. This is kind of fun talking about the speed of light. The table shows how fast light waves or electricity can travel through different materials. So when we talk about space, water, copper wire, diamond, ice, and olive oil. Of these 6 values, which is faster? Of a couple of them, light through diamond or light through ice. And how can you tell from the expressions for the speed? I think one thing that would be really helpful is to set these up in that scientific notation. We're setting it up so it's times a power of 10. With the 300 million, we can see that as 3 times 10, which would be all these powers that come after. We see 8 place values, so we can see times 10 to the 8th power. This one is already set up for the water in scientific notation. This is kind of nice. One way we can tell that is that there's only one single digit before the decimal, and that single digit is not a 0. Copper wire, what we can do with this one is we take that first digit, 2, this is what we call our leading digit, the first non-zero number. We put a decimal after that. We bring in the non-zero numbers after it. And then here's the part where we get into scientific notation. In the early introduction, we count all of the place values that come after that leading digit. all the way out to where the decimal currently is. So we look at these values and we see that this 2 8/10 would have to be multiplied by 10 1, 2, 3, 4, 5, 6, 7, 8 times. So this would be times 10 to the 8th power. Now, diamond might look like it's already in this format of scientific notation, but this finite decimal right here at the beginning has some rules. This value right here in scientific notation has to be less than 10. It has to be at least 1 and less than 10. So to make this less than 10, I need to bring my place values, my decimal, back 2 place values, making this 1 2400ths times 10 to the 2nd power, then times 10 to the 6th power, which means I can combine these two by the product of powers rule. So I get 1 2400ths times 10 to the 8th power. Ice is written in scientific notation already. I can tell because of the finite decimal. And then olive oil will be our last one, 2 times 10 to the 8th power. Now that I see all these in the same power of 10, I can just simply compare finite decimals and see which one is faster. Diamond, we see is 1 2400ths times 10 to the 8th power. And ice is 2 3/10 times 10 to the 8th power. We see that ice is greater than the value of diamonds. How can you tell from the expressions for speed? Well, when powers of 10 are equal, the finite decimal of ice is greater. And we see that here, 2 3/10 is greater than 1 2400ths. I can only compare these two finite decimals when the powers of 10 are the exact same. If the powers of 10 are not the same, then these place values, the ones, the tenths, and the hundredths, and so on and so forth, are not actually lined up. This is the critical part. If the powers of 10 are not equal, then I cannot compare the finite decimals and say that they're the same values. Okay, let's go ahead and step this up just a little bit more. And we're going to take a little zoom in onto that number line that we used. And we're going to zoom in and put these other materials on the number line here and just, or be looking at how these numbers in this table, how they interact with that same number line that we worked on. So we're going to label the tick marks between 2 times 10 to the 8th power and 3 times 10 to the 8th power. Well, what we're doing is just magnifying this section right here to figure out how do I make this bigger. And what I really need to key in on is this. Notice that the 10 to the 8th power is equal. So we know that these two place values are equal. For all intents and purposes, we can consider this as 2 and 3. And when we consider the values between 2 and 3, we understand that this will be 2 1/10, 2 2/10, 2 3/10, so on and so forth all the way through. But we can't forget this part that this is times 10 to the 8th power. All of these values will be times 10 to the 8th power. I think I'm going to alternate these because of space. That way it'll hopefully be easier to read. And I'm going to change to an X so I don't just get any confusion between the decimals. All right, we see those values now in there. We've labeled our tick marks. This one's done. Plot a point for each speed on both number lines and label it with the corresponding material. So on both number lines, when we look at this, space was at 3 times 10 to the 8th power. So we have space is here and here. We have, I think I can actually use just the first letter. So S for space. Then we have water, 2 2500ths times 10 to the 8th power. That's going to be really hard to put inside up here. It would be right here. It's water. But we can put that down here. 2 2500 is 2.25. There's 2.2, 2.3. Water would be right here. Copper wire or electricity would be 2 8/10 times 10 to the 8th power. So we'll put this one right here and label this one C for copper wire. Diamond, 1 2400 times 10 to the 8th power. That one won't go on this number line. That one has to come back in here, approximately here, 1 2400 to fit for diamond. We can see that one doesn't fit between 2 and 3 because of its value, 1 2400 times 10 to the 8th power. We go to ice and olive oil, and we're right back inside of here. 2 3/10 is the ice. 2 3/10, somewhere right around here is the ice. And then we go ahead and get into the water next. And onto the olive oil back here at 2. So that would be O and right here. Okay. There's one speed that you cannot plot in the number line. Which one is it? And you had to plot it on the number line instead. That was diamond. And then compare the values, which is faster, light through ice or light through diamond. As we saw earlier, light through diamond is outside of the number line. It's out here, and then there's ice. We can see that clear difference between the two, where we see that ice is greater than diamond. Diamond, oh, sorry, you can't see that, is greater on the number line. Okay, we can see that it's further to the right. All right, I'm going to skip. Are you ready for more? You're welcome to give that one a try. The numbers, this all goes with the Are You Ready for More? And we're going to wrap up this lesson today. There's a lot of different ways to compare two quantities. When we really look at population, this is a big place where we use really big numbers. Population, 7.4 billion people to the number of pennies in the U.S., 8,900,000,000. There's a lot of different ways to do this. We could write billions as a the billions as a decimal. We could write it as a whole number, or we can just tell that there's more pennies in 2015 than there's people. We know that these two values are written in there. The 7.4 billion, we could just look at it as 7.4 billion as 7,400,000,000. It's kind of a clear piece for us. When we write in powers of 10, we see that the powers of 10 are both 10 to the 9th power, but we see these values as 7.4 and 8.9. Only when we can only compare finite decimals when the powers of 10 are equal. For visual representations, we can place these on a number line, and we can see pretty easily that the number of people is less than the number of pennies. And I thought there was more, but there's not, and that's it. So really pay attention to, if there's one thing that I want you to really take away from this, don't compare these ones right here, the finite decimals, unless if the power of 10 is equal. That's a must-have for this to work out. So we'll get more into that as we get more into scientific notation. But for right now, recognize that powers of 10 on a number line, they can get really big. So reach out to me if you need some help. Reach out to me if you have questions. You're doing an amazing job. Thanks for working hard. I'll see you on the next one.